প্রথমে সিঙ্গেল
No, there
একটা
is no
পথের জন্য
classical path yet. Action is a functional. Action can be calculated for any path. Okay, so look at the so that is the meaning of this symbol. Action is not a function, it's a functional. So I think I have discussed it here, right? What action is. So here, this is action. Now let us see how to calculate action. What does it take to calculate action? So first of all, there is a time integral, which means you have to give limits in time. So ti to tf, suppose you take that. And then it's a time integral of the Lagrangian. Lagrangian is a function of x, which is an implicit function of time. In classical mechanics, your degree of freedom, all the degrees of freedom are implicit functions of time, right? That is how the formulation goes. The generalized coordinate q is a implicit function of time when you formulate the problem. And the goal of the problem is to arrive at an equation of motion which can be solved to get the time dependence of this quantity of the degree of freedom, right? That is the understanding. So Lagrangian is a function of q and q dot and t. So that is what it is, right? Now suppose then to calculate action, what do you need? You need the function of time, x as a function of time. Once you know x as a function of time, you can calculate its derivative. And then Lagrangian is a function of those variables, x, x dot and t. You plug those functional forms here, then you end up getting something which is a function of time. This is going to be some function of time. Is that point clear?
Yes.
Yeah, because x is a function of time, x dot is a function of time. When you give that for a specific function, for a specific path, so here I am taking a specific path, so ti to tf, the x goes from xi to xf. There can be many paths, but I'm taking, suppose I take a specific path. This specific path is this function x, and then you calculate the derivative. Then the derivative is also a function of time. You take that data, that information, and put that in here in the Lagrangian. Lagrangian is a function like half m x dot square minus potential of x, right? It's a function of x and x dot. You plug them, that functional form for x and x dot, into it. Then after doing that, after you complete this process, what do you get? You get something time dependent, right? So that I'm calling, say, f of t. After you get f of t, you integrate f of t from ti to tf, right? That would give you the result, some real value, and that is the result for action for the particular path that you had chosen, in this case here. That is the procedure. So you pick a path, usually a function is given, like for example, x is a function of time in this case. What is a function? Function is that you give a real number, which is a value of time, you get back a real number. You give a real number, through this function you get back another real number, that's the value of x. So for every value of t, you get a value of x. So the input is a real number, which is the value of the argument of the function, say t here. The output is the value of the function, right?
Yes.
But in this case, for action, that is not the case. What is going into the input? In
Function.
the entire function,
Okay.
from ti to tf. It is not one real number, it's an entire function, from within a range, within a segment, has infinite number of degrees of freedom, because you can change the function anywhere. It will give another function. So you pick every function and calculate the corresponding value of action. This is how the procedure goes, right? So action can be calculated for any moderately reasonable path, like depending on the Lagrangian. If the Lagrangian has x dot square, then the path should be such that its first derivative with respect to time should be well defined everywhere. Okay, so let's call them smooth paths. Though you could demand a smooth path should be something which has all the higher derivatives of with respect to time to be finite and well defined. It's enough to consider only the first derivative, because that's what you need to calculate the Lagrangian. So for all those paths, you cannot take arbitrary path, because if it is not well behaved, you will have trouble calculating Lagrangian. So within the reasonable class of paths, for each path, you get a real number s corresponding to that path. So that is why s is a functional of x, because it is not as an input you are giving a path, not a number. Though you could view this as a function, ordinary function as well, but for that your description has to be little modified. How?
Function space.
Yeah, you have to, so action is a normal function in the space of functions, where every point actually is given by a function. For every function you give here, there is a corresponding point in this space. This is an infinite dimensional space. For example, you could consider, suppose this is a path, right? You could consider its Fourier transform. Then there are infinite number of Fourier coefficients. How do you change the function? By changing the Fourier coefficients. Each Fourier coefficient is a real number, right? So you imagine a space where you have infinite number of coordinates, like a Cartesian system, where the coordinates are given by the Fourier coefficients. So Fourier transform can be viewed as so you have in the usual, say, 3 dimension. In 3 dimension, you give any point, say P can be written as x I hat plus y j hat plus z k hat. These I hat, j hat, k hat are unit vectors. It tells you and how far x is, how far you have to go in that direction. Y is how far you have to go. So this forms this basically is equivalent to giving the coordinates x, y, z of that point. So the coordinates of a point is basically n number of real numbers, n being the dimension of the space. Now a function, this function has a Fourier transformation. So Fourier coefficients, say an, bn, so on. These are infinite number of numbers, and if you collect them, say a1, a2, and so on, and then b1, b2, and so on, then there are infinite number of real numbers. You could view them as the coordinate in this function space representing that function. This is one way you can picturize. Okay, now in that space you are actually giving one point, not a function, because the entire function is represented by a single point there in the function space. Given a point, you are getting a real number. So action is an ordinary function in the space of paths. Now, when you give the boundary conditions, what are the paths? The space of paths is defined by the nature of the paths. By nature of the path means the boundary conditions. You have already given some fixed boundary condition. At Ti it has to be at xi. At Tf it has to be at xj. Even if you fix these boundary conditions, there are infinitely many smooth paths at these 2 points. those paths, each of those paths is a point in this space, and therefore it's an infinite dimensional space.